What saves a 250,000-ton cruise ship when its engines flatline at sea isn't a backup motor, but a hidden, low-tech failsafe that exploits a chilling quirk in physics, and it activates only when everything else dies. Modern cruise ships are floating power plants, but their greatest strength, automated self-preservation, is exactly what causes a total blackout in heavy seas. At the heart of every engine is a lube oil sump, a shallow reservoir designed to keep the moving parts slick. To maximize space for passenger cabins, these tanks are often wide and flat rather than deep. In calm water, this design is perfect, but when the hull tilts past a specific threshold, the oil sloshes violently to one side. This is where the sensor sabotage begins. The suction pumps that feed the engine are suddenly left sucking in nothing but air. The moment the ship's computer detects a drop in pressure, it executes an immediate, irreversible shutdown to prevent the engine from welding itself shut. It's a digital suicide pact, where the machine kills its own power to save its hardware, effectively turning a high-tech marvel into a drifting log because of a momentary tilt. The engines aren't broken, they're just too smart for their own safety, leaving the captain paralyzed as the ship begins a slow, unguided slide toward the coast. When a massive cruise ship loses power, the immediate instinct is to drop the hook to stop the drift. But in these massive vessels, the anchor is more than a mere parking brake. It's a psychological Hail Mary. The physics of anchoring rely on the weight of the massive chain lying flat on the seabed to create friction. In a storm, the ship's momentum and the 50-foot swells pull the chain taut, lifting the anchor's flukes out of the mud. So much so that the crew can feel the violent vibrations rattling through the hull as thousands of pounds of steel fail to find a grip. That is because instead of digging in, the anchor begins skipping, literally bouncing across the rocky seafloor as if it were a pebble on a frozen pond. It's a terrifying realization for the bridge team. They're dragging two massive steel weights that are doing nothing to slow their 4-knot slide toward the reefs. Absolutely zero contribution towards stopping the ship. If it's a rocky floor, they're literally scratching and recording the ship's path to disaster. And in the meanwhile, a second, invisible threat starts moving deep inside the passenger decks. The danger of a dead ship isn't only about what's happening outside the hull, it's also about the internal avalanche. Cruise ships are designed with a delicate center of gravity, but that balance assumes the cargo, like the luxury furniture, grand pianos, and thousands of tons of glassware stays absolutely put. When a ship loses power, it loses its stabilizers, leading to extreme rolls that reach the stability threshold. Everything not bolted to the floor becomes a sliding projectile. As tons of furniture and equipment shift to the low side of the ship simultaneously, they create a static list. This mess in the dining room is a lethal weight shift that prevents the hull from uprighting itself against the waves. And so the ship begins to lean into the storm, making it even easier for the next wave to just push it over. And at this stage, you're no longer fighting the ocean as much as you're fighting the weight of your own luxury as it tries to tip the vessel into a point of no return. Think of the interior as a hijacked weight, leaving the captain to pray that the emergency power can at least keep the sensors alive, even if it can't turn the propellers. A total blackout triggers the emergency diesel generator within seconds. This unit sits high in the superstructure to remain operational even if the lower decks flood. While it restores lighting and communication, this power is strictly regulated for life safety. It feeds the bilge pumps, fire systems, and the bridge's navigation screens. Even the lights flicker back on, allowing the passengers a sigh of relief, but it is physically incapable of turning the propellers. This means that the ship is essentially a brightly lit hotel room that is stranded in the middle of the ocean. There is no backdoor connection between the emergency grid and the main drive motors. You have a functioning radio to broadcast a mayday, but zero mechanical torque to stop the hull from drifting towards the rocks. This separation of power ensures that a sinking ship can still signal for help, but in a storm, it leaves the captain with a working dashboard and a dead engine. A powered bridge is useless without a single rotation of the propellers. The clock is ticking on a rescue mission that is about to hit a massive physical bottleneck. When waves exceed the safety limit for lifeboats, helicopters become the only extraction method. The physics of air rescue at sea is a brutal numbers game. A standard search and rescue aircraft can only hoist 15 passengers before its weight limit and fuel reserves force a return to land. With over 1,000 people on board, the evacuation time is measured in days, not hours. Each hoist is a high-stakes struggle against a ship jumping 20 feet vertically. The pilot must maintain a stationary hover, while the winch operator times the cable drop between massive rolls of the hull. If the line snags on the ship's superstructure, the tension can drag the aircraft into the deck. It is a slow, agonizing process of attrition, where the rescue speed cannot match the drift speed of the vessel. A single cable snag can turn a rescue aircraft into a secondary disaster. To stop the drift, the crew has to trick the ship's heart into beating one more time. In an attempt to bring a paralyzed ship back to life, engineers must intentionally sabotage the safety logic of the engine room. When extreme rolls cause oil to slosh away from the sensors, the solution is a slug-filled gamble. We're talking manually pumping every spare liter of lube oil into the active sumps until they are dangerously overfilled. By flooding the system, the crew ensures the suction pipes stay submerged regardless of how far the hull leans. Engineers are essentially drowning the sensors in oil just to keep the pressure gauges green. This desperate maneuver ignores every operational manual on the planet. Overfilling a massive engine at high RPM risks blowing the internal seals or causing a catastrophic crankcase explosion. However, it is the only way to trick the automation into ignoring the tilt of the storm. This high-heat hack provides just enough stability to force the massive alternators to stay online when the computer wants them dead. A single blown seal can permanently weld the engine into a block of useless steel. This restored thrust is the only thing that prevents the hull from entering a lethal shallow water trap. Restarting the engines is only half the battle, as the drifting ship usually moves toward the surf zone, where ocean physics changes. In deep water, waves move through a hull, but in the shallows, the water hits the rising seabed and trips, becoming a vertical wall of hydraulic force. This is the ground effect. Because the water has nowhere to go but up, the swells become twice as violent and unpredictable as they are in the open sea. The ocean floor becomes a jagged hammer waiting for the ship to drop into a wave trough. If the hull sinks into the low point between these waves, it risks bottoming out, hitting the seafloor with enough force to split the steel plating and the fuel tanks. The captain must use the newly restored engine torque not to sail away, but to perform a high-tension hover. The goal is to keep the vessel balanced in a surf zone where the water is often only a few feet deeper than the ship's own draft. In the shallows, the weight of the water can crush a hull against the rocks in seconds. With the engines running, now the final journey requires a 3,000 horsepower tether to survive the home stretch. The final step in this strange system of survival isn't about raw power, but about the transition to external stabilization. Once the manual oil overrides provide enough thrust to hold position, the ship must be integrated into a tether network. It starts with mechanical synchronization, where deep-sea salvage tugs become the vessel's external rudders. By connecting 3,000 horsepower tethers to specific reinforced hardpoints on the hull, the crew just made a makeshift multi-engine exoskeleton that can fight the windage of a 10-story superstructure. This tethered network acts as a remote-controlled brain for a crippled steering system. Every pound of tension is monitored to prevent the massive kinetic energy of the hull from snapping the lines. This is the final layer of the failsafe, using external torque to compensate for the internal sensor flaws that started the blackout. It's a grueling low-velocity operation where the safety of a $400 million machine is entirely dependent on the friction of a few synthetic fibers. The ship is no longer a self-contained unit, but a single gear in a massive multi-vessel machine.